Push That Rock here with Simpson Math, discussing geometric series. Let's discuss a finite geometric series. A series adds up the terms of an argument, so a geometric series adds up the terms of a geometric sequence. So I'm going to write down the sequence. The sequence has some starting number, and then if it's a geometric, you get the terms, all the subsequent terms, by multiplying by the same number. So I'm going to choose B as my common ratio, B for base, because it's the base of an exponent. So this is my common ratio, so I multiply by A. Then to get the next one, I multiply by B again. Well, B times B is B squared, and then B again. And I just keep going until I get to the last one. So this is a geometric sequence, but to make it a series, I add up the terms. So I add up all of the terms, all n terms, and that makes it a sum. And so I'm going to use S to stand for the sum that is the series. So the sum of the first n terms is the series that added up all the terms of that sequence. Now, I'm going to do a little fancy algebra and multiply both sides of that equation by the common ratio. So when I multiply both sides by the common ratio, I have to distribute the common ratio across all that. So I get B times this, I get B times that, I get B times that term, I get B times that term, and so forth and so on until I get out to the last one. Now notice all the powers are going up by 1. This first power is 2, the second power is 3, so this is going to go up by 1. Now I'm going to do a really fancy algebra trick and subtract. I'm going to take this and subtract from it this. So I'm taking this away from that. So I go S sub n minus this. And then I go this minus this. Well, A has nothing being taken away from it because there are no like terms down here. But this AB and this AB will go away. This AB squared and this AB squared will go away. This AB cubed and this AB cubed will go away. And this pattern will continue. There's even a term right before this one that was, the term right before this one I multiplied by B became A times B to the n. So even this one goes away. But this guy has nobody being subtracted from it. And so I have minus, nobody to subtract from. So I'm subtracting him from nobody out there. So he gets A times B to the n plus 1. So this is the difference between these two equations here. Now I want to know what S sub n is. I want to know what S sub n is, so I'm going to factor out S sub n over here. Well, it goes into itself one time, and it goes into this term B times. And then over here, I'm going to have a common factor of A, so I'll factor out an A, and that'll give me 1 minus B to the n plus 1. And then notice I can divide by this, and I'll have S sub n by itself. So I have A times 1 minus B to the n plus 1, all divided by 1 minus B, and I have solved for the sum of the first of the n terms in a geometric series. Now, you have to remember what the symbols stand for. A was the initial term. And B was the thing you multiplied by each time to get the next term. We call that the common ratio. It's also the base of the exponent. And so this is the formula for quickly adding up n terms of a geometric sequence in order to get the geometric series. Because remember, the series is the adding up of the sequence terms. So if you have 1,000 a sequence that's geometric and it has 1,000 terms, well, you just use this formula to add them up right quick. Now, I'm going to discuss something very cool next. Very cool. Here's something very cool. We have this formula here that we just derived. And it was pretty convincing derivation. But I'm going to ask, what if n goes to infinity? And moreover, what if B, remember B is supposed to be positive, Maybe in calculus we'll let it be negative sometimes, and we'll have to discuss that. But and for our class, b is positive. But what if it's smaller than 1? You know, some fraction. Do you remember the problem? I think it was a pixie dust problem where we had needed to know 1/4 to the 81th power. And we said that was essentially 0. Well, if n is going to infinity, this equation turns into a times 1 minus b to the infinity plus 1 is infinity over 1 minus b. Well, remember, 1/4 just to the 81st power was going to 0. So imagine some proper fraction being raised to the infinite power, just getting larger. 81 is not anywhere like 81 million, 81 quadrillion, 81 Googles. This is just going to go to 0. So this term here zeroes out. It's going to go to 0. And so if you want to know the infinite number of what the infinite number of terms of a geometric sequence add to, you just need to know the initial term and the common ratio. So 1 minus the common ratio divided up into the initial term, or the initial term divided by this binomial 1 minus the common ratio, is the sum of the infinite terms of a geometric series, assuming the common ratio is less than 1. So the famous example. So to add up, this is infinite. The common ratio is less than 1. So it should add up. To add it up, you just get the first term. Well, the first term is whatever you get when you put in 1. Let's see. If I put in 1, I have 1/10 to the 1. Oh, that's just 1/10. So that's equal to 9 times 1/10, which is 9/10. So I get 9/10. Then down here, I'm supposed to go 1 minus the common ratio. Well, the common ratio is 1/10. And so we get 9/10 divided by 9/10, which of course is 1. Math made simple at Simpson Math.